Yeah, thanks to the organizers for having us back as KITP after a long, pandemic break. I will talk about Kitaev spin liquids, but with a special flavor, monitored Kitaev spin liquids. And let me start introducing this idea of, what dynamics is, that is monitored by first saying what it's not. So far, very many talks at this conference were playing with Hamiltonian dynamics. We heard from Shankar, having a Hamiltonian is a great thing. So you look at the equilibrium or non-equilibrium dynamics of an isolated system. You have a unitary evolution, energy is conserved, and typically we are interested in finding out whether these Hamiltonians have interesting ground states. And in terms of entanglement, which will feature in this talk very prominently, we expect these ground states, if you have local Hamiltonians, to have area law entanglement structures. That's per se interesting because macroscopic entanglement, which sets apart spin liquids from everything else, falls into this category. So Hamiltonian and quantum materials. So here's our Kitaev Hamiltonian with spin 1/2. That's the left side of the slide. And now let's do something different and introduce a different type of dynamics, measurement dynamics. So we switch over to a situation where we think of our spins as qubits. And what we do is that we take those terms that we have in the Hamiltonian and we think of them as measurement operators. Yeah. So I could just measure xx, zz, and yy in some fashion. And if I do this, I'm really looking at out of equilibrium dynamics of an open system. Yeah. Evolution becomes non-unitary, energy is no longer conserved. But doing this over a long time, these measurement operations, I can create steady states that are very interesting and have way more interesting entanglement structures than in their unitary analogs. Yeah, and we will see how spin liquids or something similar to a spin liquid can emerge here on the right hand side. Okay, so monitored or measurement dynamics is what we will do, and something that you can do in these monitored systems is that you can drive transitions between different entanglement structures. Yeah, so for instance, you can vary some parameter and go from volume law entanglement, to area law entanglement, from a phase, that is entangling to a phase that is disentangling. And probably, the paradigmatic example for that, is many body localization versus chaos. Many body localized phases are area law entangled phases, disentangling phases, while a chaotic phase has volume law entanglement. Yeah. And the transition between these two types of phases, are very interesting per se. Yeah, they're quantum critical, but they're described by non-equilibrium statistical physics. We will have to use very different tools on unitary CFTs, loop models, and the like to describe them. There's a very beautiful review out this year from Matthew, Vedeka, Adam, and Saga, on this, discussing this physics in the context of circuits. Okay, so let's get to see these pictures here. So we start with a system. Initially we start with a non-super interesting state. That's some product state, and then you have some gate operation, and these gate operations shown here of unitary, and we know that unitary gates can create some sort of entanglement. And now we scramble. We put some measurements into these unitaries. And now you have a competition between measurements and gates, some that build up, they scramble the unitaries, but there's a disentangling effect of the measurements. Yeah? And that can drive exactly such a measurement into a space transition, something that Matthew invented here at Santa Barbara. And the really interesting aspect of this transition is that the volume law phase actually is stable. Yeah? Because in the first place, you would think that entanglement can be very easily destructed by a single measurement, while it takes very many unitaries to build it up. Okay, the reason that it does not get destroyed immediately is the fact that there's non-local correlations in the system that measurements cannot easily destroy, and the fact that there are these non-local correlations is what you can also use to encode quantum information in such circuits and get a quantum error correcting code. Okay, so that's a situation where we have both unitaries and measurements, and we can go to an even simpler version where we have only measurements. Yeah, so I start with a state, and I have a couple of non-commuting measurement operators, and if I all throw these measurement operators onto the state and randomly measure, I will also create entanglement. So the effect that we just discussed, there are intrinsic to unitaries and measurements, can also come just from measurements. So scrambling and unscrambling can come from these operators alone, but you have to have frustration in the sense that they're non-commuting operators. Okay? And again here, the volume law phase, can be created is somewhat unexpected. What you have to have in order to do that is measurements of more than 2 qubits at a time. So you have to have multi-qubit measurements, and then you can create structured volume law phases, something that we will see, in this talk in just a second. So that's the introduction to, this type of dynamics, monitored dynamics. And now let's apply that, to the Kitaev model and, create a monitored Kitaev model. This is work that I've done together with Nat, who's a postdoc at Caltech, and, Guyi, my postdoc in Cologne, who's, fantastic. And so here's what we have done. We have followed in the footsteps, of people also here in Santa Barbara, Ali Lavazani, Cheng Yu, and Sagar Vijay, and, the Stanford group. So we take our honeycomb lattice, now made out of qubits, and now we, randomly measure, along, the bonds, of this, lattice structure, ZZ, XX, or YY measurements. And we do so by just having 2 qubit measurements for the moment, and really no structure in space. So we randomly select bonds, and also no structure in time. So there's no patterns in any direction. We will come to a pattern version, later in the talk, but right now, we do this completely random. And then you get a phase diagram. Sure. Next slide. Okay. Okay. So I measure, I measure ZZ, XX, and YY. And what the operation is, comes in just a second. Let me first say, advertise, why this is interesting. We can draw phase diagrams, which will now talk about entanglement structures that you can generate, in the steady state of, these processes. And, these phase diagrams, are drawn as a function of the probability, that you, measure these 3 different type of operators, X, Y, and Z. So similar to, the strengths of the coupling in the Hamiltonian. And, visually you see immediately that these phase diagrams are not alike. So they have some similarities. But this famous phase diagram that we all know, becomes here replaced by one that has a circular structure in the middle. Okay, so what do we do when we measure? Well, let me first say, what we also do. So we will go beyond this circuit, by putting now an interaction term. So we go away from the free, system that we have just seen, and we add an additional term, that is, this plaquette term. And this plaquette term, is not the flux term of the Hamiltonian, so it does not commute. It's a different term. We'll see what it does. And what that, will do is, when we, now add a fourth component to our phase diagram, and we get some tetrahedron like this. And within the tetrahedron, we have very many different phases, that I will discuss now one after the other. Before that, let me explain what we do when we do measurements. So this is, again, the same structure. Where we have enriched our qubit system. So the system qubits, that will constitute, this Kitaev model are the white ones. And then we have added, a bunch of ancillar qubits on every bond. So on every bond, there's an additional qubit that I will use to measure. And the way that this works is that I entangle, this qubit here, this is 2 qubits, to the left and the right. Doing this pi over 4 rotation, with the operator Z, X, or Y, and the C naught, and then I measure this guy. And the effect of that is, is that I, effectively do a 2-body measurement, ZZ, YY, or XX. So I do a single side measurement, which I generate, do on this ancillar qubit here that, does this thing. Okay, good. Very briefly, so that we're not completely off in the imaginary, you might ask, is this something that one can realize, somewhere? Well, if you want to realize a circuit, you should go to a quantum computing device. And for instance, if you go to the IBM, devices, they actually have, lots of this already in there. So here's, the different IBM devices from the last, 4 years. Yeah, Falcon, Hummingbird, Eagle, and Osprey are all available in the cloud. You know, with 27 up to 433 qubits. This year's chip, you know, will be Condor, will be announced later in the year. Yeah, and what you should see is they have this brick wall structure. Yeah, which is exactly this honeycomb lattice, of the Kitaev model that we're interested in, and they have these interstitial sites, that we use to do the measurements. Yeah, so in principle there is a platform, to make all of this what we're discussing, possible and go in practice. Yeah, and these chips are enormously big. Yeah, so in terms of many body systems, they're very interesting.
When you said Hamiltonian, what is the Hamiltonian?
There's no Hamiltonian. We dropped the Hamiltonian on slide 1. Yeah, so all we do is we measure these operators. Yeah, and we get a wave function at the end of the day. Mm-hmm. So what is a phase? It's that all the states in that region of parameters, yeah, are all the states have all the same entanglement structure. Yeah. Let's come to an example in just a second. Yeah. Let's get some intuition about what this these operators do, and for that we go back to the Hamiltonian model that we know very well. So we know that the Kitaev Hamiltonian, yeah, with its bond interaction and this Plaquette term, we can fermionize into Majorana fermions. Yeah, we have our hopping Majoranas, we have fluxes. That's the non-interacting part here. And now this term that we add, this Plaquette term, ZZXXYY, which is different from the flux term, but commutes with the flux term. It commutes with the flux term, but it anti-commutes, these pairwise interactions. What that is, if you Majorana-rize it, is a 6 Majorana interaction term. Okay, so that's interesting. And so what does that term do? Yeah, so this term stabilizes a topological state. Yeah, it's a gapped Majorana surface code that Fu, Saga, and Tim have developed a couple of years ago, which is distinct from what you get here on this side. Which is, if you just have, the Kitaev model, it's this gapless Majorana spin. Okay? Both sides are long-range entangled and interesting, and that's what we use now, to get some intuition of what we can do when we, do this monitoring of, these terms. Okay, so we can dynamically create long-range entangled phases. Yeah, step 1, we do just, the pairwise measurements. We do, lots of the Z measurements. Yeah, and a few of the others. Yeah, what you then generate is your short-range Majorana dimers, with a Z2 gauge background. Yeah, so that's the toric code. Yeah, created dynamically now through measurements. Okay, so that's the same state that you get, when the Hamiltonian, is distorted to have, much stronger Z interaction than the other interactions. And you take, the 6th, spin term. Yeah, and measure that, yeah, you get, with the Majorana surface code, this other topological state, which is called the Colorcode, yeah, which is, more topological entanglement entropy than the other one. Yeah. Okay, so these are the two, principal players, in these limits, where one of the couplings is very strong. Now let me show you how these are dynamically generated. Yeah. So if we start from some initial mixed state, yeah, and we look at the entanglement structure of this state, in terms of the entanglement, the topological entanglement entropy as a function of time. So we keep, measuring, these different operators, then you see that dynamically, two states here start to, flatten out. Yeah, so they have, very long time stable behavior. So these are the color code and the toric code in these anisotropic limits where, certain couplings are much stronger than the others. Yeah, and these exponentially long-lived states here are what you can use as a topological memory, yeah, and that's that's exactly Alexei Kitaev's idea of the toric code, yeah, played out here now in a dynamical way. And then there are other states, which behave differently, which decay, over time, and which you want to understand as well. Okay, but let's play, with these, these topological states first, for which we have the best intuition coming, from the Hamiltonian side. Yeah, so now we can. Look at our tetrahedral phase diagram, which is spanned by these 4 probabilities of doing px, y, and z, the 3 bondwise interactions and this interaction term on the top. Yeah, and when you then just draw this topological entanglement entropy as vary these parameters, and you clearly see regimes, where, up here, where, the Colorcode interaction is very strong, you get a topological entanglement entropy of 2, yeah, and, down here, these, pockets down here, you see that you get, a topological entanglement entropy of 1, which is the conventional toric code, yeah. So you see this guy versus that guy, topological entropy goes from 2 to 1, and there is a region, where it's stable, on a plateau in that level, and then there's another region which is different. Okay, so we start to see how this phase diagram, comes about. Yeah, so pockets of, error-correcting codes, in the anisotropic limits, and then something else happening in the middle, and where exactly this middle is better, calculated using another entanglement measure, the tripartite mutual information, yeah, which gives you a nice crossing point at the transition out of these topological states to whatever's in the middle. Topological entanglement entropy sharply drops. So what does that mean? It means that you determine an error threshold, yeah, for these codes, yeah, as a function of this parameter which varies us within this tetrahedron. Okay. So how can you understand this model, in a almost analytical fashion? So let's start, with our lattice structure. That's here, and now put, the different operators that we have in our protocol, these 4 different operators, on the bonds of this lattice, and just look at that, and that gives us what's called the frustration graph. Yeah. So all the the 4 different operators, unfortunately, 2 of these colors don't come out very well as different. Whenever there's a link, they anti-commute. Yeah. So that's the frustration graph of our model. Yeah. And now, as we vary probabilities, within our parameter space here of this tetrahedron, there are special points, and these special points are these, midpoints of the edges of the tetrahedron, where, some of the frustration in this graph is lifted. The graph becomes very simple, just lines. That's where we can actually analytically solve, the model, yeah, because it's just, stacks of, one-dimensional problems, yeah, and in that case, the problem is actually self-dual, and it maps to the problem of percolation. Okay. So why is that? So these operators, if you look, for instance, the CZ operator commutes with, out of the 6 operators from the Placket term is, the guy on the left, the guy on the right, not the top and at the bottom. So that's why you get one-dimensional chains in one direction. Yeah. Then you get a self-dual point. If you go to the point and you look at the entanglement structure, yeah, you see that something interesting is happening. It's diverging. Yeah. If you plot it, yeah, and you plot it as a function of, entanglement entropy over L, yeah, you see this beautiful entanglement arc, that you know from conformal field theory, Calabrese and Cardi. Yeah, so it's L one-dimensional chains, and every one-dimensional chain, has some conformal spectrum, and we can pull out the central charge, and the central charge is the one of 2D percolation, which in this case we fully understand, analytically, and it's the first example of a non-unitary CFT in this problem. And it's one that we often see, in the context of these, random circuits. Good. So these are these, self-dual points, at, certain locations our, phase diagram, connecting, the different code spaces with one another. So these, topological phases. And now if you go to the rest of, the phase diagram, we will see all kinds of different entanglement structures. So very rich. Yeah, and now, what constitutes a phase is, that within, a phase, so a parameter region, you will have this entanglement structure, that entanglement structure, that entanglement structure, and, all over this, parameter space, you'll have the same entanglement structure. So it's a phase diagram in terms of entanglement. Yeah? Yeah, so the typical states that you get after this time evolution, will all, look alike. Okay, and you get 1D CFT scaling, volume law entanglement, and Lifshitz entanglement. So let's start, with the bottom plane. So that's what Ali Lavazani and Saga et al. have looked at here. Yeah, so the free Majorana equivalent now in a circuit. Yeah, and so this problem again, reduces, to something where we get a system that is best described, as the density matrix analog of an RVB state. Yeah, it can be mapped to a Majorana loop model. And it has, beautiful CFT scaling again. Yeah, so it's It's L log L entanglement scaling, which is different from what we know in the Hamiltonian Kitaev ground state for the spin liquid that we all know about, which has an area law. So as we go to the monitored version, we get L log L scaling, and if something has L log L scaling, we feel that it's connected to a Fermi surface, that you cut L times and pick up a log L scaling for every time that you pick up, that you cut the Fermi surface. So it feels like what we have on the bottom of this phase diagram is a spin liquid with a Fermi surface. As we now move into this tetrahedron, as we turn on the interaction term, so this Plaquet term, we get volume law scaling immediately. So no longer can we collapse this data for different system sizes, where we go from 18 to 60 by 60, so 7,500 qubits. You see that the entanglement structure gets this cusp-like structure, so that's very well known. That's a page correction, so that's volume law scaling that we induce, and we can actually track this parameter of this volume law as we go within this phase diagram as a function of this interaction term, how this volume law turns on and off again. And you see in terms of numbers, the volume law is of course the dominant in terms of L scaling, but in terms of numbers, the prefect of this volume law is very small. Well, it's big enough so that you have seen it with your bare eye. But the next sub-leading correction, this L log L, this liquid-like term, it's very big in terms of numbers. And its prefactor, varies, as you, traverse, this phase, as do all of the other parameters. But probably, these first two are the most interesting one. So you have a volume law with a sub-leading L log L entanglement structure. So that's a structured, volume law phase, that you can create, in this circuit. And that's something that is very hard to create in Hamiltonian land, so impossible. The phase boundaries, that set apart, this now interacting Fermi liquid regime here in the middle, which has, this L log L scaling, to the rest of the phase, is best determined again by this tripartite mutual information. And if you do again cuts, you see, this, perfectly, circular structure along these cuts emerge. And in reality, this phase boundary really is a sphere, squashed into the tetrahedron, which, numerically is very clearly the case. Why we have, this spherical symmetry, we don't understand. In the same way that we don't understand why we have the circle on the bottom plane. Okay, so it's nothing, that is somehow in our model, because we can point you to other papers doing completely different Clifford circles, that also have, the circular structures. So what's happening on the sphere? So on the sphere, you get a different type of entanglement scaling, which is this quantum-Lifshitz scaling, which people looked at in the context of conformal quantum critical points. Back in the day when we ran a program here on field theory and entanglement structures. So it's some complicated equation that again describes how this entanglement as a function of the cut varies, and you perfectly sit on this line. So everywhere on the sphere, you have this quantum Lifshitz scaling. So on the bottom of the plane, the non-interacting version, you have L log L scaling. You go into this ball-like spherical structure. You get volume law entanglement, and exactly on the sphere, you have this quantum Lifshitz. So you go from a Fermi liquid to an interactive Fermi liquid through a quantum Lifshitz transition into a area law entangled state. Good. So why is this all interesting? It's interesting because it allows us, to think about systems, that we cannot, imagine to solve, in Hamiltonian land. So, the Hamiltonian for the free Majorana case, the Kitaev model, is famously analytically solved. And for that, we generated a Clifford circuit and looked at that, which has its own puzzles, why it has a circular structure. And then we turned on this Majorana interaction, and you have zero chance, of solving this problem here in the upper right corner. There's a sign problem. So there is no numerical way of doing this. But in this lower right corner, in the measurement version of it, we can do everything. So it hasn't increased in complexity. So we see a problem that is still, formulated in terms of Clifford circuits. And Clifford circuits are known to be very, easy to simulate numerically. So they're, only come with polynomial efforts. So that's the Gottesman-Mills theorem. So that's why we can do them. So we can go in this direction here and look at a problem now whose Hamiltonian equivalent is very hard to understand. But making the connection between what we see, on the monitored side, so in this measurement dynamics versus the Hamiltonian dynamics is also non-trivial. So how you translate between these two rows. Some of the things that you can now do, is to weaken the measurement. So we come back to this idea of, how do you actually measure this? By using this ancilla qubit. And now let's play, with this, pi over 4 rotation, that we need to do the measurement. So if we vary this coupling, so instead of doing a pi over 4 rotation but a lesser rotation, we go from a strong projective Clifford measurement to a weak measurement. And we can ask as a function of this measurement, what is happening, to the phase or the structure of entanglement that we just stabilized? Is that surviving or not? So is there a transition, in this parameter here, going from strong to weak measurements that, will take our long-range entangled phase and turn it into a short-range entangled phase? And is there a finite threshold for that? So we could solve that problem for a similar version of this version problem here. Instead of, having 3 different types of coupling, X, Y, Z, we have Z couplings everywhere. So your ground state looks like a GHZ state, a ferromagnet, and it turned out that that problem, is analytically solvable, and maps perfectly onto what's called the Nishimori line in the context of the random one-Ising model. So that's some interesting direction, which I mention here particularly because we will have a preprint coming out hopefully next week, with people at IBM where we have seen this in experiment. Good. Let's close, with another, observation problem. Let's, play with our Kitaev model yet another time and vary the type of couplings. So now we have, a Kikuli pattern of, couplings here, of our XX, YY, and ZZ couplings. And so that's a spatial pattern. And we will also put a temporal pattern where we say, well, in the first round of our measurements, we are measuring, now all these X bonds. Okay. In the second round, we measure all the Y bonds, and then the third, all the Z bonds. And we continue like that. So why is that interesting? Well, that's interesting because our friends over at Station Q, Hastings and Ha, have found out that dynamics of rotating these measurements and doing this for a long time will dynamically generate a logical qubit. So something very powerful, coming out of this Fouquet dynamics and just 2 qubit Pauli operators. So it's another type of quantum hierarchical code that you generate dynamically. And now let's play with this idea of weakening the measurement in this protocol. Okay, so what happens? Well, so like in the Nishimori problem, so weakening the measurement will eventually destroy, this phase. So you will no longer be able to purify, your system to, in topological state. And there is some threshold which is not very clear here because, systems that we do here are very small and finite, up to 12 by 12 and, 12 rounds of measurements. But what's more interesting is, if you just look at the order parameter describing that topological state, but if you introduce a Hamiltonian to calculate an effective energy, so it takes the logarithm of the density function, so we don't really introduce a Hamiltonian, but we use something to come up with an energy and look at its fluctuation, we see this double peak structure. And this double peak structure is of course very reminiscent of the Kitaev model at finite temperature. So the effect of weakening a measurement is like going from 0 to infinite temperature. And then we see this consecutive double peak structure, which we know very well how to categorize. So the large T, so T is this rotation in the measurement operator, is where the gauge field gets stabilized. That's the low temperature transition in the Kitaev model. This is where you transition into the topological state. And this upper one, is what corresponds to the high temperature peak in the Kitaev model, which now appears in our case for, weak measurements, so small t. And that's of course, where fractionalization happens. So that's very interesting. And you also notice that, that the finite size scaling, of these peaks is also, different, from the Kitaev model, so the Hamiltonian version. So in the sense, that we strengthen the topological phase as we go to larger system sizes and not the other way around. If you look in the middle, and look at the entanglement negativity, which is another way of looking at entanglement structures, kicking out, the classical correlations in the problem, and looking only at the quantum correlations, very nice. You see that that thing actually, starts to diverge, the system size in this intermediate regime, again in an L log L fashion, which is again reminiscent of, this Fermi surface scaling. Okay. Good. So these were the two principal examples. So let me close. My time is also up. So I've discussed, two types of problems. One is, a monitored Kitaev model, and what kind of entanglement structures can we stabilize in the presence of additional interactions. A problem that we cannot do in Hamiltonian land. And then what happens, if we introduce flow K dynamics and weaken these measurements and see these signatures of fractionalization that we have seen in the Kitaev model at final temperature. And I want to close with two more general questions. One is what is that we can really learn from these monitored Clifford circuits that are so accessible to our numerics about the magnetic problem, so the Hamiltonian problem, and can we engineer the spin liquid chronology that I just showed you in one of the current platforms and actually have them come to life in experiment. Okay, thank you.
I have an extremely basic question, so I want to go back to rather early in the talk when you were talking about these codes in the limit where you're primarily measuring, let's say, the ZZ, I think, and you said that this was going to produce a toric code phase. So, and I guess what you meant, first let me just check my comprehension. Okay, you run this thing for a long time, you take the state that occurs in a particular trajectory and you measure its entanglement entropy. That's what you do, right? Yeah. You compute its entanglement entropy and you get that of the toric code. I guess the question I have is, okay, if, as I do this thing many, many times, suppose I do this many, many times, how many linearly independent states do I get for a given system size? So, for a fixed Hamiltonian, there are, presumably on the torus, there are 4 linearly independent toric code ground states. But we can find many such states with, for example, just changing the sign of some of the plaquette terms in the toric code Hamiltonians. Is the space of states that you span, what's its dimension as the...
So, okay, so let me answer this in the following way. So what we are really looking at here, is the dynamics of the Majorana fermions in the problem. So what's completely, agnostic here is actually the gauge sector. So in our case, we can start with a completely mixed state. We also don't care about the gauge structure, and we will see this effect. But what we typically do is that we actually, we start a mixed state and then we measure the fluxes. So then we know about those. And we can, we can put ourselves in a certain flux sector, like flux free, and then run the dynamics and see this, but it actually doesn't depend on that. So in that sense, I would like to say that the number of states that you have is extensive, because all these fluxes, can be just random. Okay, but the point is, that so what we really see here is the dynamics of the Majoranas, and they do what they're supposed to do. They create this entanglement structure.
And is that generic, or are there cases where it actually converges to a much smaller number of states?
Well, okay, so so you see these two separate things, the light blue and the green, So you see that in all these pockets, which corresponds to the corners of the phase diagram, you end up in exactly this number 2, and then you have a very sudden transition, to some other thing, in the liquid-like phase in the middle. And in the liquid-like phase in the middle, these are these 3 lines here. You continuously decay. So this the thing just goes down. That's the topological part, which eventually will hit 0. But in these corners, you're flat on the topological number. So you don't have to be, you know, on some special point. You know, all the states will have.
No, I'm asking about like how unique the state is that you're generating in this stochastic process. Is it?
Well, so in our case,
So I know there are protocols where people look at like dissipative state preparation, where they kind of tune the dissipation and actually target a specific state. But you're never doing this, I guess.
No.
So you target some space of states in some sense, and it's.
Yeah, which has, you know, this structure, and and the fluxes are not really participating here, because, you know, everything commutes with them, So in the such, you know, I can set that to my desired situation, you know, such as flux.
Yeah. Thanks.
Yeah.
Any more questions?
Simon, you probably said this or maybe went through this a bit quickly. Could you repeat again? It's again along the same lines as what Leon just asked. So could you explain how do you get the toric code by measuring ZZ? You only measure ZZ operators, which commute with one another, correct?
Yeah, so see, I put, you know, there's two guys in here, like this guy and that guy, this one, you know, color-wise not very good. So I'm just off, you know, the top of the iceberg, So, you know, I need, like in the Hamiltonian version, I need a little bit of that mixture of the other terms in order to get the toric code.
Wait, what do you start from? Didn't you start from a random state?
See, in the Hamiltonian version, you also know if you only have JZ, you don't get the toric code, but in the moment that you turn on, you know, a little bit of these other interactions, you know, you do it. And that's also true here. So you need a little bit of, you know, these other terms, so you have to be, you know, so in the space diagram, you have to be a little bit out of the corner, and then you get a toric code.
I see, but is it as simple as to say that when you measure, let's say slightly off the corner, you measure a little bit of x-axis, a little bit of y-y, but primarily ZZ. Are you saying that that process of stochastically just measuring randomly is morally equivalent to writing down the Hamiltonian with primarily ZZ terms, a little bit x-axis, a little bit y-y?
It's not morally equivalent, but they stabilize the same state.
Right,
and,
so
you know, and I'm starting in these corners because that's where we get the intuition and where this works. And you see also, you know, in the middle, you know, it doesn't work at all. So our intuition about what we would, you know, think we get, you know, what we get in the monitored version is very different.
I see, but the particular statement you just made is the way to prove it. I'm not asking you to prove it for me now, but is there proof that exists that if you do it stochastically near the corner, that you guarantee it, or is that more like empirical observation?
Well, so that's a question for the quantum information experts, But that's, of course, you know, my understanding, you know, that's what, you know, they know, because, you know, the way that you stabilize, you know, the toric code in a quantum computing device is by measuring stabilizers. Measuring stabilizers, not, you know, putting a Hamiltonian that is a stabilizer Hamiltonian.
I see. Thanks.
Yeah, thank you for this beautiful talk. The question is maybe somewhat related to the previous one, this relation between measurement versus Hamiltonian. You know, you mentioned there's a Majorana liquid phase through measurement process. I'm just wondering, like, for Hamiltonians of Majorana fermion on the honeycomb lattice, one can also create a phase which has a Fermi surface. You know, basically if you think about second neighbor hopping between the same sublattice, you know, there's if the hopping between the A sublattice has one chirality and the one from the B sublattice has the same chirality, it generates a gap, goes into this P plus IP superconducting state. But if you choose opposite chirality, if I remember correctly, that will generate a Fermi surface.
Yeah. So
is there any connection?
So in the Hamiltonian version, I have to break, you know, time reversal symmetry, in order to do that. So here I don't. And and the connection is really not one-to-one. So if I go to a different lattice geometry, like, you know, the Yau-Kivitson structure, I will also get, you know, a gapless state. So in terms of what the entanglement structure looks like, so it's not an area law state that I generate.
Thank you.
Yeah, thanks for very interesting talk. So one question is, probably I missed your explanation, but you compare the entanglement entropy with 1+1D CFT. So you put the 2D system on very long cylinder or something like that.
Yeah, so that's exactly true. So let me.
But after measurement, you still have mixed states. And this entanglement entropy is defined like in pure state or?
Okay, so again, what I do is, I have my 60 by 60 system, which is periodic boundary conditions. That's a torus, so I cut it, and I vary the length of this cut, so that's this axis, I look at the steady state after a long time. What happens in the protocol is, while I start with a mixed state, the effect, of measuring for a long time is that I purify, and I get a pure state, as a steady state, and the steady state entanglement, that's what's shown here.
I see. Thank you. Another maybe vague question is that you compared the measurement induced phases with ground state of Hamiltonian, and for interacting Majoranas, you did many computation for measurement induced phase, but yeah, this one. So for the ground state, there's a sign problem. So does that mean this measurement induced phase is not fully quantum, or?
Yeah, so so that's a very interesting question. So I can go here. That's first of all what I realized. Is it trivial what I get here, like classical state? Well, not at all. Because what I just told you is going from here to here, what I generate is this volume bar entanglement. So I go into a very quantum state. But it's also not a trivial Thumel state, because it has a structure, so the subleading L log L term, which makes it very clear that this is not some random Thumel state. So I have something very structured quantum mechanically here, which I can see, and which has a different computational complexity than the guy up here, and so that's really the key question, what is it that I can learn, from going here, in this context about whatever might be up here.
Thank you.
I have a clarifying question. So you mentioned that you do a lot of measurements. For example, in the Colorcode code, you mentioned that there is a T here, but that T is different from the time dynamics T you mentioned. Is that right?
So that's true. So in this particular example here, things are much simpler, and it's that I really do 1, 2, 3, 4, 5, up to 12 measurements on a 12 by 12 system, which is a very different setting. But every measurement round has very many measurements in it, which is different from what I've done before, where I've done 100 sweeps of n individual random measurements. So the problems are different.
And then you will get some steady state after doing this.
This is this statement here, of Hastings and Ha, that this this protocol generates this topological phase, this logical qubit, and that's again it's something that we see in these these calculations here, up here, so this saturation, that is exactly telling you that you're in this topological state. And this drop here, is where that disappears.
Thank you.
So in this slide, the error threshold here, is it related to error threshold of like if you actually use these weak measurements to do error correction on the code, is it related to that threshold or not?
Well, okay.
I mean,
so
I know it's an upper bound, but like.
So first of all, let's agree that this threshold versus the other threshold is the tripartite mutual information that we that from your own work. We had a nice crossing point. Here we have something drifting, so that's why threshold comes here in this quotation mark. But nevertheless, you see that as you go to larger systems, deeper rounds, this is actually going to the left. So this thing becomes more stable, which is not surprising. And what is it that is it again stable? Well, we introduce a level of decoherence by screwing up this measurement. We go from Clifford to non-Clifford, which is also the reason why these systems are so small, because it's super expensive to calculate now, And so in that sense, it's one error threshold for this type of decoherence, Whether that's the most relevant one in doing this in experiment, it's a different question, But for me, it's an interesting one because it generates this structure, So it has this temperature connection to it.
Thanks.
Okay. Yeah, let's thank Simon for the interesting talk.